today then. Look at power series, but we'll look at the use of power series, which is how we can expand a function into a series of terms, and then the more terms we add, the more accurate the answer is. Then we'll look at Maclaurin series, which is a way of finding the power series for a function. So if we've got a particular function, like we'll look at the sine function or the cosine function, something like that, we can express that as a power series using Maclaurin's series. So that's the aim of today, really, to be able to use Maclaurin's series to expand the function and find its power series. So if we start off by looking at a power series and seeing how that works, power series for the exponential function e to the x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and so on. And we'll show how that's arrived at from Maclaurin series. Okay. 4 factorial, 5 factorial, whatever else, means 4 times 3 times 2 times 1. So factorial is just a way of writing that series of multiplication down to 1. So 5 factorial, 5 times 4 times 3 times 2 times 1. And you've got a button on your calculator that allows you to find the factorial, which is an exclamation mark. Let's use this series to find a value for this exponential function and compare it with what we get on a calculator. So find e to the 0.3 using the power series for 6 terms and compare this with the calculator value is the aim. So what we're going to do is take the first 6 terms of this. So first term would be 1. So 1 term, 2 terms, 3, 4, 5. So up to the x to the 5. So in the power series, x is just the value. So it's be 1 plus 0.6 if we're finding, 0.3 if we're finding e to 0.3. So first of all, write down this power series. E to the 0.3 will equal 1 plus 0.3 plus, and so on. Write down the power series for the exponential function. What would the next term be? Right, 0.3 to the power 2 over 2 factorial, which is in fact just 2, because 2 times 1 is 2. Oops, not multiplied, plus. And so on. So that's 3, 4 terms. No. Okay, so it's just calculator practice, getting used to use those buttons. Put the series in using the fraction button and the factorial button. Write down your answer and then see if that agrees with the calculator value of e to the 0.3. Error on this series, of course, I've got carried away with the 4 and the 5, so it's 0.3 to the power 4 and 0.3 to the power 5, thanks to you all. So this equals 1.35. Three significant figures, so you've rounded it to 3 significant figures. And it agrees with the calculator value, I presume, okay, to 3 significant figures. So the power series works, and the more terms you add, the more accurate your answer is going to be. And as I say, a little bit later on, I'm going to see how that's arrived at. And it's a useful thing, because if I want to differentiate some functions, if I can write it in terms of some sort of power series, and the power series always takes this sort of form, as we'll see, that's actually quite easy to differentiate or to integrate, if you want to integrate the function. So to convert it to its power series can be useful when it comes to calculus. Also, I don't know whether you've ever wondered how the calculator works out what e to the power 0.3 is. Well, actually, what it does is runs through some sort of routine like this and works through the power series. Okay, so it's a perfect method to find the value for a function if you've got some sort of Excel program that you can run to arrive at your values. Yep, Tom. Okay, now The use of these power series can be extended, look. So instead of e to the x, we could find a e to the kx by multiplying the whole series by a, and then our term not being x but being kx. So a brackets 1 plus kx plus kx squared over 2 factorial and so on. So we can extend this power series now once we've got the exponential function for something like this. Now in the textbook, exercise 56, I'd like you to just have a look at a couple of questions on that. So if we go to exercise 56 in the textbook, which is on page 108, you can have a look at those questions in there, and if I just give you a few minutes to have a go. So for question number 3, we've got 1 minus 2x e to the 2x. So that's going to equal 1 minus 2x. Hang on. I don't know, it's really weird, isn't it? Jesus. Oh, God. Right, so what we've got then is 1 minus 2x e to the 2x. So that's going to equal, fingers crossed, 1 minus 2x. And then we can write the power series for e to the 2x, which is going to be 1 plus 2x plus 2x squared over 2 factorial, or 2 plus 2x cubed over 6. And does the question ask you just to go for it to a certain number of terms? Right, so there we go, we will stop there, okay? 4 terms. No, because I've worked out what 6 is, 3 factorial. Yeah. Now what do you think we do now? Sorry? Expand the brackets, right. So this is going to equal 1 minus 2x times 1, which is 1 minus 2x. Then 1 minus 2x times 2x, or putting the 2x first. And then 2x squared over 4. 2x squared is 4x squared over 2 times 1 minus 2x. And then for the last term, we could work out what 2x cubed, so 2 cubed is 8x cubed over 6. And then you have to multiply out these brackets. So we have to multiply 2x by 1 minus 2x, and 4x squared over 2, which simplifies to 2x squared times that bracket. So multiply out all the brackets and then collect like terms, and you should end up with the solution in the textbook. So see if you can carry on from there and finish it. And it's a similar sort of thing for question number 4. Algebra is the key here. It's expanding out the brackets. So if we carry on with this one and try and suss our way through the algebra, then we get 1 minus 2x. 2x times 1 is 2x. So you can see already that later on they're going to cancel each other out. 2x times minus 2x is minus 4x squared. So that's that one sorted out. 4x squared over 2. Well, 4 over 2 cancels down to what? 2. So this is like 2x squared. 2x squared times 1 is 2x, so that's plus 2x squared. Minus 2x times 2x squared is minus 4x cubed. That term, isn't it? What about the next term? We've now got this last term, which is this one, so that will be plus, going back to this line, 2 cubed is 8. 8 over 6 becomes 4 over 3, x cubed. So that's what that last term is. So now multiplying that by 1 minus 2x, we get 4x cubed over 3 minus 8x to the 4 over 3. And now we collect together like terms. So we see that minus 2x cancels with plus 2x. Minus 4x squared plus 2x squared just gives us 2x squared. So that's, sorry, minus 2x squared. So this gives us 1. Minus 2x squared. Then the x cubed terms, we've got 4 over 3x cubed minus 4x cubed. 4x cubed is like, if we make it into thirds, it's like 12 over 3, so that's 4 over 3. Take away 12 over 3, leaves us minus 8 over 3 x cubed. That's the x cubed sorted out, and then we've just got one term involving x to the 4, so that's minus 8 over 3 x to the 4. And barring little arithmetical slips, that ought to equal the answer in the textbook. Does it? Right, so we've made an error somewhere then, haven't we? No. Looking at the solution to this question 3 we just looked at, of course, we're missing part of the solution in the terms involving x to the 4 here. There's another term involving x to the 4, which would come if I did the next term on here. So plus k x to the 4 over 4 factorial would give us our other fourth term. So if you wanted to, at some point, you could just add that extra term and see if you now agree with the answer in the textbook. So, yeah, thanks for that, Tom. Okay. So it's okay as far as we've gone, but we should have included another term. Now, yeah, look at this next one, please, number 4. See if we can get that one out algebraically. So for question 4. Okay, so the first term then, the first step rather, write 2x to the half in front, because that's the constant really, the x to the half that it might come afterwards, but that's the constant we're multiplying this exponential function by here, putting the brackets around this. So it's 2x to the half that is our a that goes in front, and then we expand out the exponential function. 1 plus whatever the exponent is, which in this case is x squared, plus x squared to the power 2 over 2 factorial, plus x squared to the power 3, and so on. Just put it into the power series. As far as we want 6 terms, so as far as x squared to the power 5 over 5 factorial. Now the laws of indices come in. What do I do about this? X squared squared. What does that become? Add the powers, right. If you've got 1, sorry, no, not add them, multiply them, yeah. So 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So that gives you the powers. You can work out what these factorials are. And then, when you've done that, you can multiply each of those terms by what's outside the bracket, and then try and simplify it. Okay, so simplifying what's inside the bracket, we get to this, using the laws of indices, and now we just got to multiply each of these terms inside the bracket by 2x to the half. What do we do with the with the powers? X to the half times x squared, what do we do? Oh, now we add them, Tom. They're multiplying to add them up. So a half plus 2. How do we write a half plus 2? But in terms of an improper fraction, no, we wouldn't yet. We would write it not as 2.5 in this case, as an improper fraction, which would be 5 over 2, yeah. So 2.5 we'd write as 5 over 2. So this first term would turn out to be 2x to the half plus the next term would be 2x to the 5 over 2. We write it like that because later on we might want to write it as root form. The question 2.5 is 5 halves. Yep. We write it like that because at some point we might want to write it in third form, and if you remember, this would be 2. We put the root in, so it would be x to the How could I rewrite x to the 5 over 2 in this form? Nope. Yeah, x to the 5 and then the square root of. So that we might want to write it like that, we write it the power in terms of an improper fraction rather than 2.5 or something like that, some mixed number. Okay. So carry on now and just finish off these last three terms and see if you agree with what's in the textbook.